completely eliminate this effect from QCD. I'm saying a bunch of stuff I hope you've kind of heard about in particle physics here and there. I'm not expecting you to get it all. But here we're just setting it to 0 because we know experimentally it's less than 10 to the minus 10. So for all intensive purposes, QCD preserves CP symmetry. Okay, the quark fields, these are 4 spinors. Notice I've suppressed the index. Oh, look, I forgot my flavors here. I've suppressed the index for spin. So really this is a 4 spinner, this is a 4x4 matrix in spin, and another 4 spinner. And then in addition, there's an extra index which goes over flavor. So if you like to think about matrices or tensors, this is just a multi-rank tensor, these fields. And then, of course, as we discussed yesterday, you can split this into the left and the right modes. So we know we can say the Lagrangian splits up into these left and right modes in the kinetic operator. And now I've even suppressed the flavor index, except the quark mass operator mixes these left and right. Okay, now Q here stands for quark mass, not a flavor index. So I'm abusing the notation a little. Okay. So another very important concept to get in your head is in this Lagrangian, the quark mass is the only, the operator that has the quark mass in it is the only operator in the theory that breaks chiral symmetry. Right? The kinetic term, the dynamics of QCD do not break chiral symmetry. So what does that mean? That means if, for example, you were to send the mass to 0, all chiral symmetry breaking effects would have to go away, provided the regulator you use, well, let me take that back. All physical effects that are observable depend on chiral symmetry breaking would have to vanish. And so if you do not pick a regulator for your theory that respects chiral symmetry, you will then have to fine-tune to recover chiral symmetry because your regulator will have some ultraviolet cutoff, which is a really high energy scale, and you'll have to add a bare parameter to your theory to exactly cancel that ultraviolet behavior such that the sum is 0. So we don't want to do that. We want to pick a regulator that respects chiral symmetry. And this argument also applies to QED. And if you didn't have a flavor summed over, you wouldn't call it a chiral symmetry, you'd call it a left-right symmetry. It's this U1 symmetry, but only the vector component of the U1 is a real symmetry. And it's really more like a discrete left-right symmetry than a continuous rotational symmetry, the chiral symmetry, because the U1 axial is not a symmetry of the theory. So you're just left with U1 vector, so you don't have this full left-right symmetry. So it's really a discrete left-right symmetry. But if you have multiple flavors, like we do in QCD, then you get this continuous global symmetry. And that's important. Okay. So what does it mean? That means when you calculate corrections to processes, for example, if you wanted to calculate a correction to the quark mass, some quantum correction to the quark mass is going to have to be proportional to the quark mass itself, to some power. So that's a powerful idea. If you're doing a calculation, on pen and paper, and you're trying to calculate the self-energy correction of a quark or an electron, and you find something that's not proportional to the mass, either you're using a regulator that breaks chiral symmetry or you've made a mistake. So that's a way to check yourself. Okay, so now we want to imagine the quark masses are very small. And you should ask, small compared to what? Well, small compared to intrinsic scales in QCD. That's the thing we want to compare to. And just very roughly, the dynamical scale of QCD is the proton mass. It's 1 GeV. So things that are less than 1 GeV are small. So that's what we want to compare to. So if we have some number of flavors and we ignore the quark mass term, then our Lagrangian has an SU number of flavors left cross SU number of flavors right continuous global symmetry. So there's not like a gauge symmetry, which is a local, you do local transformations of the fields. This is a global symmetry where you would do a rotation on your flavors everywhere in the universe at once. So if this theory has, okay, so first of all, I'm ignoring this. This microphone keeps cutting in and out, so forgive me if my volume goes up and down. Maybe that's better for you because you're sleepy after lunch and then you're up and then down and quiet and noisy, and it can help. So this Lagrangian really has a U left cross U right symmetry. The vector component of this left-right symmetry, which is when the left and the right rotations are the same, the U part of that, the U1 part of that is baryon number, and that's conserved in QCD. The axial component of that is, as we discussed, Amy discussed yesterday, not a symmetry of the full quantum theory. And so I'm just going to ignore the U part and just talk about the remaining SU part. So this is a SU NF left cross right symmetry. So what would be, what should you expect if the theory has a symmetry? Like what might you expect? Well, the first thing you would expect is this left-right symmetry you can actually show has implications for parity. And so you'd expect degenerate parity partner states in the spectrum. So what does that mean? So you would expect the nucleon mass, which you know is about 940 MeV, and the negative parity nucleon mass to be the same, but the negative parity nucleon mass is 1510 MeV. And so we can ask, well, what's the size of the splitting? Well, that's almost 600 MeV out of 900, so that's not a small correction. So this is a very large splitting. What else do we observe? We see that every single hadron made of up and down quarks, and strange if you want to count it, all the hadrons have masses that are on the order, I'll just say 800 MeV. Like the rho is 770, the nucleon's 940, the delta is 1200, which is a resonance. Except for what? There's three particles that have a very small mass, the pions. The pi 0 is 134 point something. The pi plus and minus are 139. And so these masses are very small compared to the other hadron masses that come out of QCD. So why are these three masses so small when everything else is heavy? That's a clue for what's going on. And why don't we see these degenerate parity partner states? And so if you remember, if you have a global continuous symmetry that's spontaneously broken, you get massless particles, the Nambu-Goldstone modes. And so if you recall the U1 version of this, let's say we have some complex field, phi 1. Now here we'll test my artistic abilities. We have the potential. And then what you find is that when you spontaneously break the symmetry, the vacuum no longer respects the symmetry. So the theory has spontaneously broken in some random direction. We'll just set that direction along the phi 1 axis, because we're free to choose the axis. And then you get these massless modes that go around the minimum of the potential. And these Goldstone modes represent the quantum fluctuations of the angle of the vacuum from one space-time point to another. So that's how you exchange these massless particles. And then you can reparameterize these complex fields as some radius and an angle. Excuse me for a sec. I think I'm inhaling the chalk dust from the new piece of chalk. Okay. And so then what you find is the mass of the row is of order, the vacuum expectation value, and the mass of theta is 0. Okay. So, and what else do you know? There's going to be one massless mode for every generator of a symmetry that's broken. And so what do we know? In QCD, the pions are odd parity, intrinsically odd. And there's 3 of them. So if I'm thinking about a 2-flavor theory, then I've gone from a left-right symmetry, which has 3 generators for left and 3 generators for right. And I have 3 mass parity odd states that are very light. So that must mean I've broken the axial symmetry. And it's a little bit of the axial group is not a real Lie group. So just like if you remember when you're doing Lorentz transformations and you look at rotations, the generators of rotations transform into each other under the commutation relations, but the generators of the boosts give you actually a rotation generator. In the same way, the axial generators, the commutators of those give you a vector generator. Whereas the vector group is a real group, the axial group is not a closed group. But we often just say we break the axial symmetry, but really what you should say is you're taking the left-right symmetry and breaking down to the vector subgroup. But everybody in the community gets sloppy in their language, and I will do the same. So we've broken the axial symmetry, and that's why we have these very light degrees of freedom. Because remember, the quark masses are not 0, they're just small. So maybe I can think of the quark mass as a perturbation about this spontaneous symmetry breaking that's happening from the QCD vacuum. So we have this SU NF left. In fact, so that NF, Vafa and Witten wrote an article, half a century ago, proving that when you have a vector gauge theory, that when it spontaneously breaks, it must break down to the vector subgroup. So any theory like QCD, if it spontaneously breaks, it has to break to the vector subgroup, and it can't break to the axial. I think there might be some small corrections to this work. Don't quote me on that. But I remember the Vafa-Witten proof that you have to break to the vector subgroup. Okay, so what do we have? Going back to our QCD Lagrangian, I'm going to look at the derivative term. And now I'm going to change notation because that's what I apparently did. So now Q is a quark field and no longer just a flavor index. And so under these transformations, the right-handed quark field goes to here. I'm just repeating a lot of what was discussed yesterday. And then these right and left generators we have some right, and now it's a vector because I have 3 generators. And this is a vector of SU2 matrices. Here, let me focus on 2 NF equals 2. So then these generators are just the Pauli matrices over 2. So, for example, what is a particular rotation you can imagine? Consider rotation angle theta. Here, I won't specify if it's left or right, but consider theta as 0, pi 0. And so what does this mean? So then our rotation, say a right-handed rotation, would be e to the I pi over 2 times sigma 2. And you remember how to express your exponential of Pauli matrices in terms of cosines and sines? Maybe, maybe not. It's from quantum mechanics, since we all learned that. This is cosine pi over 2 times the identity minus I sine pi over 2 times sigma 2. And so what is this matrix? This you can show is just 0, -1, 1, 0. So what does this particular rotation do? It takes an up and a down quark and changes it to a minus down and an up quark. So this is a symmetry. If you took every up and down quark in the universe and you perform this transformation, you wouldn't be able to tell. Which is a lie, because there's also isospin breaking corrections in the standard model, which is in the universe. But if it's just QCD, you wouldn't be able to tell. And this also in SU2, just to repeat, the vector subgroup of SU2 is isospin symmetry that you're used to. The proton and neutron being very similar in mass, why the pions are all very similar in mass. This is isospin symmetry, the vector subgroup SU2. Okay, so now let's consider this peculiar quantity. I'll call omega ij, which is going to be a q bar right, j, q left I. So what is this? This is going to be some dimensionful number times delta ij, which is not going to be 0. Okay? So this is specifically what we call the order parameter for spontaneous chiral symmetry breaking. So this vacuum expectation value is not 0. This is how QCD is causing the theory to spontaneously break. And so now if we look under the rotations, so some generic left-right rotation, what do we get? We get Q, now R, K. Now we have a rotation matrix. But then I can take these left-right matrices outside, and then the vacuum expectation value is just going to be, like if I take this piece and this piece, I'm going to get lambda delta KL. And so then this is going to be R dagger KJ L I K lambda, or you can write that as just a matrix. So if theta R equals theta L, which is to say R equals L, then this is just the identity. So it's invariant. So it's invariant under vector transformations. Otherwise, it's not invariant. So the vacuum has broken the symmetry. And oftentimes we'll say, I'll use this shorthand for spontaneous symmetry breaking, because it's much shorter to write, just like my little squiggle for my name. Okay, so what is lambda? Well, what's the dimensions of lambda? What's the mass dimensions of lambda? I can't hear you. There's like a fan. Did you say 1? Nobody said 1, right? 3, yeah, of course. It's 3 because we have 3 halves and 3 halves, so lambda must be 3. So lambda is some number that's lambda QCD cubed. Okay, we haven't talked about lambda QCD. How many of you are familiar with the definition of lambda QCD? So I'll just do a quick aside. It's a very hand-wavy thing. You can actually rigorously define what lambda QCD is, which we're not going to do here because you need a full-blown lattice QCD calculation. But it is something that you can rigorously define. But you recall hearing about the beta function of QCD, presumably. So if here I plot some energy scale, Q squared, and it's something that's defined in the space-like separation of QCD, or you could think about it going to Euclidean space where Q squared is only positive. And on this axis, I have the strong coupling as a function of Q squared. And then if you look at the behavior of QCD, the coupling, lambda QCD is defined at some order in perturbation theory where the coupling goes to infinity. And it's just a hand-wavy feeling for, it's a way to say when has the coupling become large. Well, certainly when it goes to infinity, it's become large. And so your perturbation theory is not working. And so because it's running logarithmically, it's running pretty fast here, but it's a good approximation for where the theory becomes non-perturbative. And so the mass of the proton, for example, is lambda QCD times some number. That's just something to remember. And lambda QCD, sometimes people say it's 200 MeV, sometimes they say it's 500 MeV. It's because it's a very vague, squishy concept. It depends on the order and perturbation theory you've worked. But you can define this number, strictly speaking, in some order and perturbation theory where the coupling goes off to infinity. Okay, so inspired by this picture of spontaneous symmetry breaking, where we describe the massless modes as some angle, and the massive modes is some, so this is the radial excitation is rho. How much energy does it cost to roll up the potential? And then theta is the mode that runs around the circle. So inspired by this picture in U1, we're just going to do the same thing for the pion fields. So we're going to say we have some hadronic field, which is sigma 0 times sigma. And sigma 0 is going to play the role of this radial excitation plus the vacuum expectation value. And then this sigma field, we're going to write as the exponential of I times some dimensionful field. So we have to divide by some other dimensionful scale, f, which we'll figure out what f means. And theta is just going to be a matrix that has the pions in it. It's a traceless matrix, so you can also write theta as the sum over the generators, some pi fields times the generators. What's that? Phi? I said, yeah, it's phi. I said theta. It's phi. So this is for NF equals 2. I just have this matrix of pionic fields. What do we know about F right now? The only thing we know about F is it has mass dimension 1 at this moment. That's all we know. Because I wanted my theta field, my phi field, to be mass dimension 1, so I could connect my familiarity with complex scalar field theory. So what are we going to do with this field? I assume most of you haven't stuck your fields in exponentials, then try to construct a Lagrangian. If you're familiar with this, hopefully you don't get too bored. And if you're not, hopefully you find you learn something. Okay. So we're only interested in studying the low energy excitations. So we're not going to worry about the sigma 0 field. Because the sigma 0 is going to have an energy scale on the order of the vacuum expectation value, which is going to be something like lambda QCD. So that's going to be too high energy. That's going to be an energy scale where we're going to have to worry about the quark and gluon degrees of freedom, which we don't want to do in this theory. We're just looking at the low energy effective theory. Okay, so how do we build a Lagrangian with sigma? So also notice sigma, because it's the exponential of a matrix, sigma is going to be a matrix as well. So what is the rules for effective field theory? We have to build every operator which is allowed under the symmetry transformations. So what do we do? Gauge invariance. This is the color. Well, this one's trivial because there's no color indices on our fields. So it's automatically gauge invariant. Easy. Okay, what about chiral symmetry? What we're going to do is have sigma transform as sigma goes to left, sigma r dagger. And this is motivated by our vacuum expectation of q bar q. So can we build an operator that looks like sigma, sigma dagger? Well, we can. But that's trivial because it's just going to be proportional to the identity. And now again, it's a matrix, so it's not one, but it's a matrix identity. So what do we have to do? Well, we know we usually write down kinetic operators for our fields, so let's try multiplying derivatives onto this thing. So let's consider d mu sigma dagger. Now if you do a chiral transformation on these fields, what do you get? Well, you get d mu L sigma R dagger, d mu R sigma dagger L. Now, these are global transformations, so I can pull the left and the right transformations away from the derivative. So the R dagger trivially cancels, and I get left with d mu with an L out front, sigma, d mu sigma dagger, and an L. And also, unless explicitly stated that it does, you should think of derivatives as only acting on the field immediately to the right. So there's not a nice way to write that down without getting a little verbose with the writing. So unless explicitly stated, derivatives don't behave like you know they should and multiplicatively go across everything. They only act on the field immediately to the right. Okay, so this operator is not invariant because I missed a dagger somewhere here. There's this leftover L dagger. So how can we fix this and make it invariant? Trace, exactly. These are matrices, so all I have to do is take the trace of this operator. And then under the trace, I can bring the L dagger back around and it goes away. So now, also, very common in the literature, you'll see this written with square, or not square, but an angle bracket. Writing this low is challenging my something. Okay, so here's our operator. Okay, what is the mass dimension of this operator we've written down so far? Is it dimension 4? You guys got to speak up a little. I'm also getting old, so my hearing's going. Also, yeah, one time, no, it doesn't matter. So, what was it, yes or no? Was mass dimension 4? It's not 0 because I got some derivatives. Each derivative carries 1 mass dimension. 2, because sigma is an exponential, and this is a dimensionless number, so sigma better be dimensionless, exactly. Okay, so this can't really be our operator. We have to multiply it by some unknown number. We got to figure out what that number is. So now we have our lowest order chiral perturbation theory kinetic operator. It's going to be some thing I'm going to call C2D, and then I got the trace D mu sigma dagger. So what is this? How are we going to figure out what this is? It's just some unknown number at the moment of dimension 2. So what would you think to do to figure out what it is? You must have written down a real or complex scalar field theory before, right? So what's the kinetic operator for a complex scalar field theory? Do you guys remember? Who doesn't know what I'm talking about? Raise your hand. No. Oh, who does know what I'm talking about? Raise your hand. Maybe that's the right way to ask it. Nobody? Okay. So, complex scalar field theory. Remember, d phi squared. There's a 1 here. There's no number, right? And if I had a real scalar field, what would I have? 1/2 d mu phi d mu phi. So when you construct a Lagrangian, you want to canonically normalize the kinetic operator. Because that's how you understand how everything else makes sense, is we have this kinetic operator Don't ask me why it's a half and a 1. I don't remember right now, but I do remember that it is 1 or a half. And so I'm going to match this Lagrangian to that. So how do we do that? Do we have anything that looks like these kinetic operators? We're going to do some perturbation theory. That's what we're going to do. So I have this sigma field. And now what we're going to do is we're going to continue small angle fluctuations about the identity. That's the sigma field. And I think you can guess what the sigma dagger field is. Okay, so now we got to stick it in with those kinetic operators. D mu acting on 1. What is that? 0. Great. So the first non-trivial term will be d mu acting on phi. And I want to build something that looks like d phi, d phi. So looking at this, you can immediately see the only thing you need to keep to figure out what this coefficient is the first term from both expansions. Because every have too many fields, or you have a derivative acting on 1, etc. So now our Lagrangian is going to be this C2. I'm going to have this trace. I'm going to have, there's a plus I and a minus I. Those cancel. There's going to be a 1 over f squared. And then I have d mu phi, and this trace. All right? So, and then there's higher order terms, which I get to ignore for now. And now also introduce some more notation that is often used. Oftentimes, we'll just write phi dot to mean d mu phi. And so then you might rewrite this as and now I'm also just, I know I have an upper and a lower index, so I'm not worrying about it. So this is just a way to shorthand, quickly get to the answer. Remember what phi is. Our matrix phi, did I erase that? Oh, here we go. So what's the square of phi? Well, I get pi 0 times root 2 pi minus times pi 0 root 2 pi plus. I'm going to be interested in the trace, so I don't care about what the off-diagonal terms in the square are, just the diagonal ones. You can convince yourself the lower one is the same thing. So then what do you get? C2 d, the trace, I can do the trace. I said, what do I get? 2 pi 0 dot squared plus 4 pi plus dot pi minus dot. Now, the pi plus, pi minus are complex fields. If I take the conjugation of pi minus, I get pi plus, which you can see if you take the Hermitian conjugation of the phi field, the pi plus and the pi minus go into each other. And if you think about how the generators are acting here, I've used the plus and the minus generator, and the plus and the minus flip. So if I want to canonically normalize the pi plus and minus, I need to take out a 4. And I get left with 1/2 d mu pi 0 plus d mu pi plus d mu pi minus. And this is what we expect. The pi 0 is a real scalar field. So I expect the half, where I have a 1 for the charged pion. And then you can see C2 must be f squared over 4. So there we go. We figured it out. I wouldn't really call that matching, but we're determining what this low energy constant is. So now my Lagrangian, sorry, this is chiral perturbation. I don't remember. Let's do this. Actually, I can't remember how I wrote it. And, oh, right. I was going to put a 2 here. This 2 is just reminding us that we have 2 derivatives, and it's going to come in when we talk about power counting. So now my leading order Lagrangian, F squared over 4 times the trace of d mu sigma dagger. And now something you can see also is if you were to keep including more terms, you would not just generate a 2-pion field configuration, but you would also have, in principle, you looking at this, you might think you have 3-pion fields, 4-pion fields, et cetera, when you start multiplying these out. An interesting emergence of G-parity is you can actually show all odd pion field operators are going to exactly vanish. That's because, again, the parity of the pions, they're intrinsically parity odd, so you can't have an odd number of them. All operators in Lagrangian have to be scalars under all the symmetries, so there has to be an even number of pions. And so if you carefully work it out, you'll find all the terms like d phi and d phi squared, those will exactly cancel when you include all the terms. But you can see you're going to generate vertices that will give rise to interactions, because you can have a 4-pion field come out of this operator. Okay, what is this F? We have to talk about the F. Hopefully it is not your grade on Friday. I'm also very glad I don't have to take tests anymore. One time when I don't remember if it was a postdoc or something, I think it was a postdoc. And I thought, oh, you know, I want to go take this class from this person on campus who's like really smart and whatever. And I sat in the class for like 2 days. And I can't do this. You guys should take advantage of this time in your life when you have the energy to actually take classes and learn as much as you can. Okay, so what is F? Okay, so recall from spontaneous symmetry breaking, there's this rule. I think it's called Goldstone's theorem. That if you have a Nambu-Goldstone boson, there's going to be a non-zero matrix element between the vacuum and the current of one of the broken generators. So what does that mean? That means we have a vacuum expectation value here now 0. I'm putting in, this means the vacuum. I have some current. I'm not going to specify what it is, other than it's going to talk to one of my Goldstone modes. And this is not going to vanish. And in fact, you can show it's going to be equal to the momentum times some constant to make the mass dimensions work out. In this case, I got a dimension 1 for the pion field, dimension 1 for the current, so this V is going to be dimension 1. Okay. So in QCD, we say we break down to the vector subgroup, which means the current we're going to be looking for is an axial current, because it has to be one of the broken generator currents to talk to our Goldstone mode. And so remember, axial means theta left is minus theta right. So what do I want to do? So up to an overall sign, there's an unphysical sign. I can define my axial current as my right-handed current minus my left-handed current. So now how do we figure out what these currents are? What we're going to do is we're going to apply Noether's theorem. And I think, does she have the umlaut, or is that just, is it the wrong language? I'll write it out. So we're going to use the symmetry transformation of the theory to find the conserved quantum number, which is this conserved current. And so what does that mean? L is this e to the minus I theta L dot T. Same thing for the right, similar, except I have a theta right. And what do we do? If you recall, we consider a very small transformation, so we can do perturbation theory and just expand. This is approximately 1 minus I theta dot T. Ignore everything else. Stick this into our Lagrangian. I guess I'll go back over here. So I have my Lagrangian. I want to apply this left transformation. Then I get d mu. Remember, sigma goes to L sigma r dagger, but I set r to 0. And then if you recall, the trick is you pretend for a moment that the transformation actually does depend on space-time, so the derivative will act on the transformation. We can ignore the one. Okay, so let me say, I'll do a couple things kind of quickly, but the L, remember L is this 1 minus I theta dot t. The 1 is just going to give me back my original Lagrangian. So if I take the 1 out of both of my transformations. And so I'll just say, recover my original Lagrangian. And then I want to look for the change. And so the change is going to be captured when the derivative hits theta instead of the sigma term. So if I can remember, I'm going to have minus I d mu theta, and then I'll just look at my notes. I won't try to do it in my head. So I already forgot my f squared over 4, so let me put that back in. Now I'm going to put an A, because I'm just going to act on one of the generators. And then I'm going to have a trace of minus a generator times sigma d mu sigma dagger. And then another term plus d mu sigma sigma dagger t. So I have to keep the symmetry generator inside the trace because it's a matrix. And so then the theorem tells us that the current is everything that multiplies the derivative acting on our little transformation. So here, then we can see that J mu left is given by, how did I write it? Plus I f squared over 4 So now I'm putting these little parentheses as a reminder that the derivative is only acting on the first term. Oh, look, I'll just jump to my last equation. Oh, I put a minus. Look, I got these minus signs left and right. All right. Okay. Now you can do a similar operation and get the right-handed current. And I'll just write the answer for you. So here's our left-handed current. And then you can construct the right-handed current. And you get plus I f squared over 4 And just dumb little tricks I do. The reason I pulled this minus sign out of the left-handed current is because I know I want to take the right minus the left. And so if I put a minus sign out front, I can just add them. So I can help reduce the chances I make a minus sign mistake. Yeah. Yeah, that's, so I erased it, but that's our original Lagrangian. Oh, sorry. After we do all this, we set sigma to 0. Sorry, theta. Sorry, hold on. The terms, you want derivatives acting on, sorry, okay. I just realized I completely misunderstood the question. Please ask it again. Two derivatives on the theta. So that's going to be second order. We're only interested in the linear response. So we're considering very small angle rotations because we want to look for the linear response to match the current. Okay. So then I'm going to take my right minus my left. And what you can show is, well, first of all, there's no nice way to write this. But we do remember that we just expanded these sigma terms, right? Like if I look at these terms, I can't quite combine them neatly because the t's don't show up in the right place to just have two terms in the end. But if I do a small phi expansion of the sigma field, I can do that. And then you get four terms. So d mu minus I phi over f. And here, then I can take the 1 out of the sigma field. I am definitely breathing chalk. And then we can get the 1, and then we have a d mu I phi over f from the second term. Then I get a plus. There's a 1. But you can see as I've written it, well, maybe it's because I knew what to expect. I've set it up so all the terms with the plus and the minus sign line up next to each other. At the end of the day, what do you get? You get f t d mu phi. So this is our axial current to leading order in the small field expansion. So again, we're also looking for a linear response in the pion field. So let's do something explicit. Let's consider TA 0, 1, 0, 0, otherwise known as T plus, the raising operator. So if I put in the raising operator, what do I get? Then my axial current is going to be F. Now, this is 0, 0, 1, 0 acting, and again, this is just my phi dot. So it's going to pick out just the pi minus field, right? If I multiply this by, on the left, 0, 1, 0, 0, this is the only surviving piece, the pi minus. And so I get F root 2 d mu pi minus. So this is the axial current of the plus, the plus generator. Okay, so then what do? We can go back to our equation and see what this means. So now I have a vacuum expectation value of J mu A plus on some pion field, and this is not equal to 0. So then I have root 2 f d mu pi minus. So can you tell me what pion field this has to be? This is meant to be a B, to be a B. What B is this B? What's the only non-vanishing contribution? Again, I can't hear anybody. I can only hear myself. You guys are too quiet. So you guys need microphones. I'll walk over there since you're actually saying something. What? Yeah, which one is it? Yeah, it's plus or minus. It can't be 0. So if I have some field phi, how else do we know how to write that? I can write that as the creation operator acting on the vacuum. And this I can think of as a creation or annihilation operator, in fact, because it's a complex scalar field. But let's look at this and think of this as an annihilation operator, because usually this would annihilate a pi minus. Okay? So if this will annihilate a pi minus, what I need this state to be is a pi minus. So 0 root 2 f d mu pi minus, and then this is going to be a pi minus creation operator acting in the vacuum. And a pi minus creation operator is a what field? I think somebody said something. Again, it's a pi plus, okay. Very good. Yeah, because again, the Hermitian conjugate fields to each other. So the pi plus field can annihilate a pi plus or create a pi minus. And so what is this going to be? Well, now we have to do a little Wick contraction algebra. So there's only one way to contract the fields to get them into normal order so they don't vanish. There's only one way to do it, so I'll get a 1. This, we're going to talk more about these derivative interactions, maybe not so much detail today, but we're going to talk about them. So this derivative is going to bring down momentum of the field. If again, it's as simple as just write the Fourier decomposition of the field, and you can see how the derivative just moves inside the integral and picks up a momentum. And the thing to keep in mind is one way you can always get the answer correctly is you can always just think about the annihilation operators of your fields when you think about what the derivatives do. And then you just have to pay attention, is my field coming into the vertex or out of the vertex? So here, what do we have? We have something that looks like a field coming. Oh, here's another thing I learned. Most of the time, it doesn't matter. But sometimes it does. And what is it? It is, I always draw time going this way when I'm thinking about writing a Feynman diagram. And this is actually something I got from Ann Nelson. And the reason is, if you write your diagrams from right to left, then the way you write down your operators when you have multiple vertices you're sticking in will correspond to the exact same way you would write them in a matrix element. And once in a while, when you get that order wrong, there's a relative minus that will create get the wrong answer. So I encourage you, it's just a way to foolproof yourself a little, always write your diagrams going this way. If you don't like it, don't do it. But this is a way I have eliminated minus signs in my life. So I have a field coming in. It hits this axial current. So if it's an incoming field, what does that mean? So if I'm having this derivative act on an incoming field, and I'm only thinking about using the annihilation operators in my field content, if you remember the Fourier decomposition, if I have some pi of x, I write that as the d3k over 2 pi cubed, and then you have the annihilation operator, and if you're the mostly minus metric and Minkowski space, which is what I work in. You have a minus I k dot x, and then you have plus the creation operator e to the plus I k dot x. So if you have a field coming in and the derivative hits it and you're picking up, you're only using the annihilation operators, minus ik is the rule. I guess I said we'll talk about it later. I just talked about it now. This is how you can determine this is minus I called it k. Over there I called it p. I'll just switch back to p. P mu from the momentum of this pion field coming in times square root 2 f. So this is the matrix element. And this is what f is. And it's called the pion decay constant. So this is measured experimentally, although there's some subtleties with measuring it, because once you add QED corrections to the beta decay process where you can measure it, you can actually no longer cleanly define this vertex without introducing some regularization scheme dependence. But we're in pure QCD for now, so we can ignore that. We're not turning on QED, and this is a very well-defined quantity. Again, it's called the pion decay constant. It's a little funny because this is a property of QCD, this F. It has nothing to do with weak decays, but it was measured in weak decays, so it got the name the pion weak decay constant. So just a little bit of knowledge. So, and then at the underlying level, what's going on, you have this pion decay. Here's a fun problem that has nothing to do with what we're talking about here. But how many of you have worked out the rule of why a pion preferentially decays to a muon instead of a pion? And if you are wondering what I'm even asking, it's because the electron is so light compared to the muon, you would think the phase space factor would favor pion decaying to electrons. Because ME over MU is like 1 over 200. And the amplitude's going to go, I think, with the fourth power of the mass, or the decay rate. And so you'd think there'd be a factor of 200 squared enhancement for the electron phase space. But the pion predominantly decays to the muon. So here's a bonus question having nothing to do with this school. If you haven't worked out that problem, you should figure out why the pion preferentially decays to a muon instead of an electron. And it's related to chiral symmetry. I'll just give you that hint. So it's kind of like, am I running out of time? Oh. Oh, okay, that's okay. I was more ambitious than I had imagined. I'll just finish. What was I saying? Random stuff. So we got a pion. It's got some quarks. In this case, it was the pi minus. So I have a D bar and a U quark. No. There's a U bar and whatever. The content is U bar D. The creation operator is UD bar, but the content is U bar D. I have a pion coming along. This down quark emits a W boson, turns into an up quark. This is a flavor changing decay. And then this W spits off an electron and an electron neutrino. And so this is the decay that's actually happening, how the pion decay constant is measured, and the amplitude is proportional to this QCD matrix element of a pi minus times the leptonic current, which is the weak decay on the other side, times VUD. I have to convert a down quark into an up quark, and this is done with the reason the weak eigenstates and the QCD eigenstates aren't the same, so I get this CKM matrix element. There's a 1 over square root 2, and then there's this G Fermi that you worked out yesterday after we left the class, right? This was the assignment I gave everybody, so you figured out what G Fermi is. So, okay. And then in this normalization, F is about equal to 92 MeV. And the reason I point this out is because the literature is riddled with inconsistencies. Most of the time, big F means 92. Little f is the square root of 2 times big F, which is about 131. But then there's big F Weinberg, which is equal to big F, which is equal to square root of 2 little f, which is equal to like 180 MeV. So if you're reading Weinberg's book, he's using his own normalization because he does everything his own way, or at least he used to. And now we have the little f, which is the bigger number, and the big F, which is the littler number. And the reason I've forced myself to use this one is because we observe when we compare chiral perturbation theory to experimental data, this big F is going to play the role of the UV scale. And if I use the big F, then it turns out to be phenomenologically the correct value for what we call the chiral symmetry breaking scale, which we'll talk about next lecture, because I ran out of time today. Okay.
All right, let's thank André.
I didn't get to a loop integral yet. This is terrible.
Same problem with Sebastian. Are there any questions, comments, or discussion topics for André? Let me bring this to you.
Why can I say that a matrix that has zero trace can be written as the sum of generators?
Oh, all the generators are traceless.
What?
All the generators are traceless.
Okay, so
These are the generators of SU2 Lie algebra. I should have been more specific. It's not the generators of a general matrix, which would include the identity, which is, I think, what you're thinking. But these are specifically the generators of SU2.
okay.
So, we have the TA, TB, what is this?
Okay, so that's not a property that can be generalized to any traceless matrices.
Yep.
Okay.
If we included the U1 in the, remember in the beginning I said I'm going to ignore the U1 part of this U left right. So if you included the U1, let's say the axial U1 transformation was not or was a real full symmetry, then this matrix would also include a term proportional to the identity.
And there you made a Vic contraction
Yeah.
from pi minus and pi plus, but it's the derivative of pi minus, right? That you're making a contraction with pi plus. Okay. Just to make sure that I'm
So
following.
yeah, when you're doing the Wick contractions, you can ignore the derivative. You just have to remember where the derivative was so that when you're looking at the Feynman diagram, you know what field is having a derivative act on it. So you can, if I label this momentum P, then that's why I get this P.
Okay.
So when we get next time, when we have multi-legs and only two derivatives, then we'll see how, and just like Sebastian was talking about yesterday, you have to count which P is the derivative acting on.
Okay, thank you.
You find the pi on the k constant. You can calculate the pion mass by the Gelman-Oaks-Henner in that way, thinking so you can get back to the Lagrangian and get that. But I'm just a little confused because in the first Lagrangian, you're thinking about U up and S quarks.
I was being general in the beginning,
Oh,
including UDNS. And then when I got down, I wasn't going to do algebra with 3x3 matrices in pen and paper. So my mathematical license is expired. And out of laziness and principle, I don't want to support Mathematica, so I haven't renewed it. But I haven't learned how to use SIMPy yet, so I was forced to do 2x2 matrices. So I did SU2.
But I'm thinking, where is the scale of your theory? So where is the something like
The UV scale.
Yeah.
Yeah, that's going to be related to F. And what we're going to find, we call it the chiral symmetry breaking scale, the UV scale, and it's going to be 4 pi F.
Oh, yeah.
And that's going to come out when we actually do loop graphs. We're going to see that emerge. And first I got to put in the quark mass, show you how the pion mass comes out, which I was going to do today, and I didn't.
Okay, thanks.
Any more questions? Nobody? Okay. And we have coffee break now until, let me double check, 3:45, in which the exercise session will begin.